All right, in this video I will be working number 6 from 2021 BC free response. Okay, so this is a series question that says, okay, the Maclaurin series for g is given by g of x as the sum from 0 to infinity of -1 to the n, x to the n, divided by 2e to the n plus 3. And what's actually going to happen is they're really not going to do much with the fact that it's a Maclaurin series. Besides, you find the interval of convergence and do the alternating series test. But for now, we're just going to be talking about 1 over e to the n, which, as you probably know, is a geometric series with common ratio 1 over e, so it clearly converges. But they want you to show that it converges using the integral test. Okay. So what we're going to do is we're going to remember the conditions necessary to use the integral test. Well, I need the function, the summand, I need it to be continuous, positive, and decreasing. Okay, so what I'll say is f of x equals 1 e to the x, which from here on out I'm pretty much just going to be calling e to the negative x, is continuous, positive, and decreasing from 0 to infinity. You do not need to justify that. On 0 to infinity, right? I just stated the conditions. Use the integral test to show that that converges. All right, well, what we're going to do is we're going to use the integral from 0 to infinity of 1 over e to the x dx, so e to the negative x dx. Okay, and we remember that this is an improper integral, and we don't have an option here. We have to transform it into a limit in a free response setting. Okay. So this is the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx. Okay. I don't think you need to be looking at the problem right now. I'm going to say that this is equal to the limit as b approaches infinity of, okay, an antiderivative for e to the negative x is negative e to the negative x as x runs from 0 to b. Okay. I think that this is actually easier to write as a fraction, right? Especially to think about the limit as x goes to infinity or b goes to infinity or whatever. So I'm going to call this -1 over e to the x in general. So I'm really going to do the subtraction and start calling it as a fraction. So this is -1 over e to the b minus -1 over e to the 0. And this limit, okay, that goes to 0 as b goes to infinity. The denominator gets real big, the fraction gets real small. Minus -1 over 1, okay, so minus -1, that's equal to 1. And so I'll say, since the integral from 0 to infinity of e to the negative x dx converges, the sum as n runs from 0 up to infinity of 1 over e to the n also converges. Okay. And that's part A. Then in part B, they're going to say, use the limit comparison test with the series the sum of 1 over e to the n, which I just showed it converged, to show that the series g of 1, which is an alternating series, converges absolutely. Okay. Okay, for this part, g of 1 is an alternating series. And if we want to take an alternating series and show that it converges absolutely, what we need to do is we need to take the absolute value of its terms and determine if that would still converge. So I'm going to just kind of tell the reader I'm checking the sum from n equals 0 to infinity of the absolute value of -1 to the n over 2e to the n plus 3. To determine absolute convergence. Okay, I'm not sure. I feel like this is necessary, but I'm not 100% sure. There might be some thing about the limit comparison test that I'm not exactly thinking of right now that would make this not necessary. But what I'm going to do is I'm just going to say, all right, I'm going to consider, well, I'm going to start by saying I just showed that the sum from 0 to infinity we just showed that the sum from 0 to infinity of 1 over e to the n converges. Even if you were not able to do that in part A, I mean, I don't know if they're going to be looking back and making sure you import the correct answer. Oftentimes they don't. So if you could just claim that we showed it, even if you weren't able to compute the integral or remember the conditions or whatever, you can just say we showed that this converges in part A. Okay, now I'm going to consider the limit as n goes to infinity of the ratio of the terms of this series to the terms of that series. And if that limit is positive and finite, as in it is greater than 0 but less than infinity, then we will be able to say that they have the same converging diverging behavior. And because I know this one already converges, I'll be able to say that that one converges. Well, I guess I'll be able to say that that converges, which means that that one converges absolutely. So the limit as n goes to infinity of this thing's absolute value, so I'm going to say 1 over 2e to the n plus 3 divided by 1 over e to the n, so that's like multiplied by e to the n over 1. That limit is equal to 1/2, right? Because the biggest thing I see on top is 1 e to the n, and the biggest thing I see on bottom is 2 e to the n. That limit is 1/2. And I'm going to say that number is positive and finite. Which gives me that the sum from n equals 0 to infinity of 1 over 2e to the n plus 3 converges because it has to have the same behavior as this one, because the limit of the ratio is positive and finite. And since I've shown that this converges, I am saying that the sum from n equals 0 to infinity of negative 1 to the n over 2e to the n plus 3 converges absolutely. It's kind of a lot of analysis, and I'm not 100% sure that all of that is necessary, but that's what I'm going to be writing down right here, because I've got plenty of time. Now in part C, they're going to ask us to determine the radius of convergence of the Maclaurin series for G. Well, I'm going to copy that back down. G of x equals the sum from n equals 0 to infinity, 1 to the n, x to the n, divided by 2e to the n plus 3. All right? And what I'm going to do, let it adjust to the light, and I'm going to run the ratio test on this thing. And I don't want the full interval of convergence, just the radius. So I'm going to try to get it down to x divided by a number. Its absolute value is less than 1, then that number I'm dividing by will be the radius. Okay, so I'm going to consider the limit as n goes to infinity of the ratio of the n plus first term to the nth term. So negative 1 to the n plus 1, x to the n plus 1, over 2e to the n plus 1 plus 3. And then I'm going to divide, I'm also taking the absolute value here, divide by these terms. So that's going to be negative 1 to the n, x to the n, and then 2e to the n plus 3. All right. Yeah, and so now what I'm going to do is I'm going to start, canceling stuff off. These negative 1s, these are just not going to matter because I'm taking the absolute value. Okay, I've got n plus 1 x's, and then but just n down here, so all but 1 will be killed off. And then so what I'm left with is the limit as n approaches infinity of, well, x is pretty much all I'm left with, times, this is 2e to the n plus 3 over 2e to the n plus 1 plus 3. What I'm going to do is I might factor out a power of e over here and might write this like that. 2e to the n, let's see, plus 3 divided by e, I guess, when I factor out, factor out 1 power of e from there. Okay. And this thing here that I'm going to, I don't know, I guess highlight, I'm using a highlighter. This is going to go to 1 because, you know, the biggest thing in each term is 2e to the n. Its limit as n goes to infinity is 1. Okay? 'Cause they essentially are the same. So what I'm left with is equal to the absolute value of x divided by e. And with the ratio test, in order for this to converge absolutely, we need this to be less than 1. So here I am. I'm to the point where I can say, based right here, I'm going to say radius is equal to e. And that's part C. All right, now part D is probably simultaneously the easiest and most tricky part of this problem. It's easy in the sense that it's just the alternating series error bound. We know how to do that. We're just going to plug in the next term. It's tricky because n starts at 0, right? And they say the first two terms. So they want you to plug in n equals 3 here. But we're not going to do that. We're not going to fall victim to that trap. What we're going to do is we're going to say first two terms are n equals 0 and n equals 1. So it's like n equals 0 is 1 over 2 plus 3 is 5 minus n equals 1, okay, negative 1 over 2e plus 3. And then that means that the error is less than or equal to the absolute value of the next term. Well, the next term would be where I plug in n equals 2. So negative 1 to the 2 is 1 divided by 2e to the 2 plus 3. And walk away, right? We're done. That's all I've got to say about this one. This one's a little tricky because of, you know, there's some subtlety in it. But in some sense, you know, don't forget about the alternating series error bound. That one's there. They're supposed to, it's there to hopefully get you some credit if you know what to do. But that's all for this one.